Next, synchronizing power. Represented with PS. And synchronizing power, it is the term associated with synchronous power P when the machine is subjected to disturbances. This is the term associated with synchronous power P when machine is subjected to disturbances. And how this synchronizing power acts depends upon the type of disturbance. So if the disturbance is from the mechanical input side, then PS will act as active power. If the disturbance is from the excitation side, then PS acts as reactive power. So how it acts as active power and how it acts as reactive power will be better understood from the parallel operation of alternators, which will be discussed in next topic. Simply, synchronizing power is that which helps the machine to attain synchronism when the machine is subjected to disturbance. Once the disturbances are clear, PS will be 0. Suppose the disturbance is from the mechanical input side. So when the disturbance occurs, PS will act, it will act as active power, and what it does means it will make the machine which is having more mechanical input as generator and the other machines as motor. So is why once the disturbance is clear, PS will be 0. Suppose the disturbance is from the excitation side, then PS will act as reactive power, and what it will do means the machine which is having more excitation, it will demagnetize that, and other machine it will magnetize that. So is why it will maintain the balance. So once the disturbance is clear, then PS will be 0. So this is how the synchronizing power will help the machine to be in synchronism by clearing the disturbances. And this will be better understood from the parallel operation of alternator. And PS is given by PSY into change in delta, where this is the change in load angle due to disturbances. Now let's move to the parallel operation of alternators and know how it acts as active power and how it acts as reactive power. Next, parallel operation of alternators. So what is the necessity of running the alternators in parallel? Why? Because with increase in load, we need to supply more power, so that alternators are to be connected in parallel so that the power for the extra load can be met. But before paralleling, certain conditions are to be checked. That is, certain conditions are to be followed. Let's see what are those conditions. Conditions for parallel operation. First, same terminal voltage. Means, suppose if there are two generators which are running in parallel, and let this be having a terminal voltage of E1, let this be having a terminal voltage of E2. If they are having different voltages when they are connected in parallel, then there will be a difference in the voltages, and because of those differences, circulating current will flow, and because of those circulating currents, machines might get damaged. So is why before connecting parallel, we have to check the terminal voltages. So in order to avoid those circulating currents, we have to operate the alternators which are having same terminal voltages, that is E1 is equal to E2. Then no circulating currents. Next, same frequency. Suppose if the machines are having different frequencies, one machine is having frequency of F1 and another machine is having frequency of F2, then what happens means there will be vector differences created. Suppose the machines are having same frequency, then there will be no vector difference between the same phases. Suppose the machine are having different frequencies, then there will be some vectorial difference and which will be increased further, and with this circuiting currents will flow and will damage the machines. So is why the other condition to be checked is whether the frequencies are same or not. Next, phase sequence. Before connecting the machine to the lines, phase sequence also to be checked. That is, let us suppose this is the existing system phase sequence and this be the phase sequence of alternator R by B, and R must be connected to the R and Y must be connected to Y and B must be connected to B. Then only our phasors will look like this. This is R, Y, B, and let the phases of alternator be R dash, Y dash and B dash. So this is R, Y and B. So if the incoming generator is connected to the existing system with the same phase sequence, then the phasors look like this. There will be no any EMF differences here. Suppose the incoming generator is connected to different phase sequence. Suppose R is connected to Y and Y is connected to R and B to B. This is our existing system phase sequence, and this is the phase sequence of the incoming alternator R dash, B dash and Y dash. Now observe, between R and R dash there is no any voltage difference, but observe here between B and B dash there is a phase difference of E phase, and between Y and Y dash there is a voltage difference, which means that because of this again circulating currents will flow and which will damage. So these are the conditions which are to be checked and followed before connecting the alternator or machine to the existing system. That is, first, same terminal voltage, same frequency and same phase sequence. Synchronization. Synchronization, it is the method of connecting a machine to the existing system by satisfying the conditions of parallel operation. That is called as synchronization. There are two methods to find out whether synchronization is done or not. Those are lamp methods and synchroscopes. Synchroscope is simply a meter, directly tells you the phase and frequency. Whereas lamp methods, here there are two methods, 3 lamps simultaneously bright and simultaneously dark method, and then 1 dark and 2 bright lamp method. Now let's discuss the 3 lamps simultaneously bright and dark lamp method. For that, let us suppose this is the existing system phase sequence, and let our incoming generator be having a phase sequence of R, Y, B, and the lamps are connected between the R and R dash. Let the lamp be L1, and the second bulb is connected between Y and Y dash, and third bulb is connected between B and B dash. Now let's see the phasors. This is the phase sequence of the incoming generator. So at this position, as between R and R dash there is no any difference in voltage, so the bulbs connected between R and R dash will not glow. Means if the phasors are like this, then all the bulbs will simultaneously go dark, and the bulbs to goes simultaneously bright, then R and R dash must be in exactly opposite direction. Y and Y dash must be in exactly opposite, and B and B dash must be exactly opposite. That is, look like this. So this is R dash, and this is Y dash, and this is B dash, and this is simultaneously bright position, and this is simultaneously dark position. Suppose if the machine is connected to the existing system, then if all the bulbs goes simultaneously dark and simultaneously bright, then it will indicate that the phase sequence of alternator and the existing system are same. So simply close the switches. But if the bulbs doesn't glow simultaneously dark and simultaneously bright, then it will indicate that the incoming generator and the existing system phase sequence are different. Then what to do? So simply reverse the phase of the incoming generator. And the drawbacks of this method are: once the bulbs are simultaneously dark or simultaneously bright, then the switch must be closed at the middle of the dark position. But if the switch is closed other than the middle of dark position, then there will be some circulating currents which might damage the machine. So here the identification of middle of the dark position is difficult, because at 1/3 of the voltage between R and R dash, or Y and Y dash, or B and B dash, bulbs will not glow, and which we might think that it is the dark position, and if in that case, if we close the switch, then circulating currents will flow and will damage the machines. So is why it is difficult to identify the middle of dark position. And second, by this method it is difficult to find whether the incoming alternator is having more speed or less speed. The incoming generator speed is more or less, and these two drawbacks are overcome in the next method of one dark and two bright lamp methods. Now let's see that method. Means here one light will be dark and other two lights will be bright simultaneously. Let this be the phase sequence RYP of the existing system, and let us suppose R dash, Y dash and B dash be the phase sequence of the incoming alternator. Here the bulbs must be connected in different way when compared with the previous case. In the previous case of 3 lamps simultaneously dark and bright method, if the 3 bulbs are simultaneously dark and bright, simply close the switch in the middle of the dark, and at the same time flickering rate, that is beat rate, must be as low as possible. Then we have to close the switch. Flickering rate means, or beat frequency means, the change in the frequency of the incoming generator and the existing system. So the drawback in that system is that we can't identify the incoming generator whether is fast or slow, and that can be overcome here. Now connect bulb L1 between R and R dash, and next bulb L3 between B and Y dash. Now let's see the phasors. Suppose L1 is connected between same R and R dash. So this is Y and this is B, and this Y dash, and this is B dash. Now observe, L2 is connected between Y and B dash. Between Y and B dash, or L2 is there, and between B and Y dash, L3 is connected. So let us suppose if L1 is dark and the remaining L2 and L3 are bright, then the darkness middle of light L1 can be identified the exact brightness of the other bulbs, so that here the exact middle of the darkness can be identified, so that we can close the switch at that instant. And next, suppose if incoming generator is slow, that is, existing system is fast. Now let's see the phasor diagram for that. If suppose this is our existing system RYP, and which we are taking it as fast, means R dash, Y dash and B dash are the incoming generator phasors. As here the existing system is fast, then R will appear like rotating in this direction. Now the sequence of brightness is, observe here between Y and B dash there is maximum voltage difference here, means the bulb here will glow bright. Then the bulb contributing Y and B dash is L2. So sequence of brightness is L2, next L1 and L3. Next sequence will be, and obviously these are running in sequence, so the sequence will be followed like this: L1, L3 and L2, and next L3, L2 and L1. And sequence of darkness, simply L3, L2 and L1, and L2, L1, L3, next L1, L3 and L2. Here the sequence of brightness and sequence of darkness are same, because the bulb which is bright first will be the dark last. So the same phase sequence is followed here. Next, suppose incoming generator is fast, means existing system is slow. Then the phasors will be like this, and we took this as R, Y and B, and now R dash will be here, Y dash will be here, and B dash will be here. And the bulbs connected between Y and B dash is between Y and B dash is L2, and the bulbs connected between Y dash and B, between Y dash and B is L3, and obviously this is L1. Observe here now, L3 is more, so next L1, L2, next L1, L2 and L3, next L2, L3 and L1, and simply next sequence of brightness is continue the sequence of darkness, that is L2, L3, L1, next L3, L1, L2 and L1, L2, L3. And the second drawback from the first method is that incoming generator is fast or slow can't be identified, whereas from this method, by the sequence of brightnesses or by the sequence of darknesses, we can say whether the incoming generator is fast or slow. So this is how the drawbacks from the previous method is overcome in this method. Next, parallel operation of two alternators on no load condition. And here there are two cases, that is changing excitation with P input constant, that is mechanical input constant. And the other case, changing mechanical input with excitation constant. So now let's study first case and then second case. That is A. Consider two alternators running in parallel with no load condition, and the prime over torques are constant, and here the variation is from excitation side. Now let this be the generator G1 and this be the generator G2. If G1 excitation is increased, then what happens? The induced EMF of generator E1 increases. Let this be the induced EMF in generator E1 and let this be the induced EMF in generator E2. Let us suppose because of disturbance, the excitation of generator G1 is increased. Means that induced EMF E1 has rise to E1 dash. So this is the circuit diagram which represents case A. And here observe that for parallel operation, the one of the condition is E1 must be equal to E2. So if E1 is equal to E2, then there will be no any circulating current. But now let us suppose because of some disturbance, that is disturbance from the excitation side. Okay, if generator G1 induced EMF has increased, means if excitation of generator G1 is increased, then induced EMF E1 will increase. Let it be raised to E1 dash. So now E1 dash and E2 are not equal. When they are not equal, then there will be obvious circulating current will be flowing in this loop, and let that be ISY. Okay. So now this is E1 and let this be E2, as both are operating parallel before disturbance. Now when disturbance occurs from the excitation side, means we consider that excitation of generator G1 is increased. So when excitation of generator G1 is increased, then induced EMF in E1 has raised to E1 dash. So now because of that, the circulating current ISY has flowed to this induced EMF. This circulating current will be lagging. So like this it will act, and obviously circulating current will lead the induced EMF E2. Now observe here, as P1 is equal to E1 dash into ISY cos angle between E and ISY is 90, as cos 90 is 0, so real power is 0, and let us suppose P2 is equal to same E2 into ISY, and angle between E2 and ISY is 90, which implies 0. And now consider reactive power. Q is equal to Q1 is equal to E1 dash ISY into sin 90. So this is sin 90 is 1. So E1 dash ISY, and reactive power of second generator is E2 into ISY sin 90, that is equal to E2 into ISY. Okay, from this what you have to note that as in case of generator G1, okay, current is lagging with E1 dash. Means here generator G1 armature reaction is demagnetizing effect. So G1 is demagnetizing effect. And whereas in this case, current leading means magnetizing effect, means G2, this armature reaction is magnetizing effect. And here the other point to be noted is that real power is 0 and reactive power 0, means power is present, and that power we call it as synchronizing power, means the power which is existing during the disturbances, we call it as synchronizing power. And here synchronizing power is of reactive nature. And from this topic, what you have to understand is, during the case of disturbances, that is from the excitation side with mechanical input constant, if the disturbance causes the increase in excitation of generator G1, then synchronizing power will come into picture, which is of reactive nature, and it will demagnetize the generator G1 whose excitation is increased because of disturbance, and it will magnetize the other generator. So that because of demagnetizing and magnetizing effect by the synchronizing power, okay, equilibrium will be reached after some time, and which is said to be that synchronizing power will help the machine to be in synchronism, and after the disturbance is cleared, synchronizing power will be reduced to 0. Why it is reduced to 0 means, as E1, E2 will be equal, so there will be no circulating current, means there is no ISY, means there is no real power, reactive power. Here in this case, reactive power, so there is no reactive power. So this is how the synchronizing power, okay, which we discussed about it in the 14th content, will help the machine to be in synchronism. Next, B case, change in mechanical input with excitation constant under no load condition. So this is the two alternators which are running in parallel, and having excitation constant. Let the induced EMF be E1, E2, and this be generator G1 and G2. And here is the case of the change in mechanical input with excitation constant. Now means the disturbance is from the mechanical input side. Let the disturbance on generator G1 make the P input, means mechanical input, increase. Then what happens? As you know that this is E1 and exactly opposite E2, and now because of disturbance on the generator G1, as the disturbance is from mechanical input side, as the mechanical input power is increased on generator G1, means there will be no change in the value of the induced EMF, but the E1 will shift to this side, like it be E1 dash, and the resultant is ESY, and to this exactly 90 degrees lag ISY. And now the real power P1 of generator G1 is E1 dash into ISY, cos angle between E1 dash and ISY is almost very low, so that take it 0, which implies E1 dash ISY, and real power of the generator P2 is E2 into ISY into cos angle between E2 and ISY, okay, let it be 180 degrees, that implies minus E2 ISY. As here real power is positive, it is generating action, and here real power is negative, which means motoring action. And from this what you have to understand is that because of the disturbance from the mechanical input power side, synchronizing power has come into picture, and it is making the generator G1, whose mechanical input power is increased because of disturbance, to run as generator and the other machine as motor. And let us see the case of reactive power. E1 dash ISY sin 0, which is obviously 0, and Q2 E2 ISY sine 180 0. Means here the synchronizing power is of reactive nature. As I mentioned in the 14th content that synchronizing power is the important and beautiful concept which tells you that by varying the mechanical input that only real power will be varied, and by varying the excitation only reactive power is varied. And how can we justify that? And for that the answer is this. Next, two alternators in parallel with load. Now as we are considering the case of load, here comes the picture of power factor. Here also there are two cases, that is change in excitation with Pmec constant, and the second case change in mechanical input with excitation constant. So now let's discuss about a case, and here the change in excitation and mechanical input power is constant. From the previous discussion of no load case, what it is understood, the disturbance is from the excitation side, then the synchronizing power will be of reactive nature and it will help the machine to be in synchronism by clearing the disturbance. And it is also understood that by varying excitation only reactive power is varied. So let the generator G1 real power be kW1 and reactive power be kVAR1 and apparent power be kVA1 and armature current IA1 and power factor be PF1. As here only excitation is changed, means real power is constant, means kW1 is equal to kW2. And now let us suppose the excitation of generator G1 has increased, which means kVAR1 is increased and obviously kVAR2 decreases. And as kVA is the resultant of kW and kVAR, as kVAR is increased, kVA will increase, and here kVAR2 decrease means kVA2 decreases and IA1 increases here and IA2 decreases. And here observe that power factor is equal to kW by root over kW square plus kVAR square. As kVAR is increased, power factor will decrease, and similarly here PF2 will increase. Now let's see how the phasor looks. For generator G1 kW1, and let this be the initial kVA1, that is phi1, and as kVAR1 is increased, okay, this is kVAR1. As now kVAR1 is increased, means now the resultant is this, means the power factor angle increased to phi1 dash. This is the kVAR1 dash. Means from this, as power factor angle increased, means that is as phi1 is increased, which implies power factor decreased. That is what this is. Now consider the phasor for generator G2. If this be the kW2 and let this be kVAR2 and the resultant is kVA2, and once the kVAR1 of generator G1 is increased, then kVAR2 is decreased. That means initial power factor be phi2. Now as kVAR2 is decreased, let this be the kVAR2 and this is kVAR2 and this is the kVAR2 dash, and the power factor angle now be phi2 dash. Now observe that power factor angle is decreased, which means power factor increased. Now consider the B case. In B case, the change in mechanical input with excitation constant. Excitation constant means kVAR1 is equal to kVA R2, and the other factors, kW1 is increased, which means kW2 is decreased, and kVA is increased, means kVA1 and kVA2 is decreased, and here IA1 increased, IA2 decreased, but power factor, as power factor directly proportional to the kW is increased, and here PF is decreased. Now let's see phasor for this generator G1 and generator G2, and let this be the kW1, and initially as kW1 is increased, let this be increased to kW1 dash. Okay, so initially this is kVA R1 and the resultant is kVA1 with angle phi 1, and now as kW1 is increased, kVA R1 is equal to kVA R2 initially, means now the resultant is this. Now observe that power factor angle is decreased, so as power factor angle is decreased, PF increased. Now consider case for generator G2, let this be the initial kW2 and this be the kVA R2 and the resultant is kVA2 and the power factor angle will be phi 2. Now from the second case, kW2 is decreased, means now kW2 is here, and as excitation is kept constant, kVR2 is dash, let this be dash. Okay, kVR2 dash is constant, and now the resultant is this one, so kVA2 dash, and observe here that power factor angle increased, so as power factor angle is increased, power factor decreased. And from this what you have to understand is that during the case of disturbances from the input side, that is from the mechanical input side or from the excitation side, synchronizing power will come into picture and it will clear the disturbance, and once the disturbance is clear, it will reduce to 0. And now after the clearance of disturbance, if you want to increase the frequency of the system, then increase the steam input of any one of the machine, that is either increase the prime mover 1 input or either prime mover 2 input, so that the set frequency will increase. Now if you want to maintain the frequency constant, then what you have to do, with increasing the prime mover input of one machine, you have to decrease the prime mover input of other machine, so that the frequency is maintained constant. Suppose now if you want to increase the voltage level of the set, then what you have to do, increase the excitation of any one of the machine, so that the voltage level will get increased. Now if you want to maintain the voltage level constant, then what you have to do, with increasing the excitation of one machine, you have to decrease the excitation of the other machine. So this is how the voltage stability and frequency stability are maintained. Next, when alternator connected to infinite bus bar, and from this first let us discuss what is infinite bus bar and what are the three modes of operations depending on the reactive power, and then the case like alternator when connected to infinite bus bar and supplying no load, and under that case let us study the three modes of operations depending on the reactive power, and then we shall study under loaded condition, and for that we shall draw the V and inverter V curves, and next the case of the alternator when connected to infinite bus bar and loaded condition with mechanical input power change and excitation constant. First let us discuss what is an infinite bus bar. Infinite bus bar is considered as the voltage source with zero impedance and with infinite mechanical rotational inertia, which means there is no change in voltage and frequency, even though the excitation is changed or even though the mechanical input has changed. There will be no change in voltage and frequency in case of infinite bus bar. Q is equal to P by Xs into E cos delta minus V. So there are three modes of operations. That is, first case, over excited means when E cos delta is greater than V, and the second case, under excited when E cos delta is less than V, and the third case, normal excitation, that is when E cos delta is equal to V. So here comes the important concept to be discussed to understand all these three modes of operations. So in case of infinite bus bar, here voltage will not change. In order to maintain voltage constant, air gap flux is maintained constant. So in case of over-excited machine, in order to maintain air gap flux constant, the machine will demagnetize. Means here the armature reaction is demagnetizing effect. As it is demagnetizing effect, which means that under over-excited case, machine is operating under lagging power factor condition. And as E cos delta is greater than V, which implies Q is positive, which means positive means Q is delivered. Now let's summarize this under over-excited case. Means here demagnetizing effect and machine is operating under lagging power factor case and Q is positive. And next let us discuss about under excited case. So if it is under excited, then in order to maintain air gap flux constant, if air gap flux is maintained constant, voltage will be constant. So in order to maintain air gap flux constant under excited case, then magnetizing effect takes place. So as here magnetizing effect, which comes under that machine is operating under leading power factor case, and here E cos delta is less than V, which means E cos delta less than V means Q is negative. Now let us summarize this under excited case. Means here magnetizing effect taking place and machine is running under leading power factor case and Q is negative, which means absorbing. And the third is normal excitation case. As here E cos delta is equal to V, which means that Q is 0. As Q is 0, which means here there is no absorbing of reactive power or delivery of reactive power, which means there is no magnetizing effect and there is no demagnetizing effect. Only here present is cross magnetizing effect and operating under UPF, and Q is 0. And now let's discuss about cross magnetizing effect. As we know that phi m main magnetic field, and let this be E, and let this be the lagging power factor case IA, and this will have two components. One component IA sin phi, okay, and the other is IA cos phi. Means this represents the demagnetizing effect and this represents the cross magnetizing effect. Under over-excited condition, if the machine is not operating under pure ZPF lag, then it will have both demagnetizing effect and cross magnetizing effect. So demagnetizing effect This is the component which takes care of the constant flux phi r, and this component, cross magnetizing effect, is the reason for torque production. Means under these three modes of operation, okay, in order to maintain constant flux phi r, okay, these components take care of that to maintain constant flux phi r, which means voltage V is maintained constant, whereas the other effect is also present simultaneously, that is cross magnetizing effect, and this is the reason for the torque effect of change in excitation with mechanical input constant under no load. Means this is infinite bus bar, and to that our machine is connected, that is alternator, and this is the mechanical input power, and this will be the excitation. So which is change, which is varying. As it is under no load, the power delivered will be 0, means active power delivered is 0. Now let's discuss about the reactive power case. That is, first, normal excitation. So under normal excitation, which implies E is equal to V, and we know that Ia is equal to E minus V by Zs or Xs, okay, and as here E is equal to V, which implies Ia is 0. So as P is equal to VIA cos phi implies P is 0, and Q is equal to VIA sin phi implies Q is 0. So under the case of normal excitation, both real power and reactive power supplied by the machine is 0, and so under this case machine is said to be floating. It neither giving power nor taking power. Next, let us consider the second case, over excitation, as E is equal to V plus JIA XS. So over excitation case means E cos delta greater than V, which implies here, let us take E greater than V. Under over excitation case, what we have seen that in order to maintain constant flux phi, the machine is operating as lagging power factor. Let us see the phasors. V and Ia will be like this, and as E is greater than V, E will be here, means Ia lags behind V, and as it is no load, so pure ZPF lag. And let's see the real power. P is equal to VIA cos 90, as it is 90, which implies cos 90 is 0, and Q is VIA sin 90, that is equal to V into I. And as here E is greater than V, means Q is positive, and Q is positive means which implies delivery. Next, the third case, under excitation. So in this case, E cos delta is less than V, and let us take E is less than V. So from the earlier case study, what we have seen that under excitation case, machine operates as leading power factor, means here current Ia will lead the V, and here V is greater than E means V will be here and E will be here, and it will be less than by the Ia access value. And here machine is operating under pure ZPF lead, and P is equal to VIA cos 90, here 0, and Q is equal to VIA sin 90, that is equal to V into Ia, as E is less than V, which implies Q is absorbed. So from this, what you have to understand that when the alternator under no load is connected to the infinite bus bar, then under normal excitation case, it will supply no real power, not reactive power. And whereas in over excitation case, Q is delivered. Whereas in under excitation case, Q is absorbed. Next, effect of change in excitation with mechanical input constant and on load. So this is the infinite bus bar to which our machine is connected. Let this be the alternator salient pole type. And to this is the prime mover input and this is the excitation input. So effect of change in excitation. So here excitation is variable and Pmec is constant, means prime mover input is constant, so that here real power, that is active power, is constant, whereas Q is either delivering or absorbing, which depends on the excitation. As we know that as mechanical input is constant, which implies that active power is constant, and in this term V and Xs are constant, that implies E sin delta is constant. Remember this. And then active power, another equation is VIA cos phi, and here V is constant, that implies IA cos phi is constant. Using this and these conditions, now we will draw the phasor diagram for this. And one more equation here we must know is, here E is equal to V plus J IA axis. Okay, so let us take this as the terminal voltage V, and now this will be the current IA, and initial power factor be phi 1. And now observe here that to represent the JIA axis drop, so which must be perpendicular to the IA phasor, means perpendicular to this JIA1 axis. Okay, let it be IA1. And now V plus JI axis, resultant is on E, so represent E1. And now take the constants, as here E sin delta is constant. Okay, and we know that angle between E and V is delta, which we call it as power angle or also called as load angle. So as E sin delta is constant, now I am projecting this E along this direction, which is E1 sin delta, and if I project E1 along V, okay, so which represent E1 cos delta 1, let it be, or power angle delta 1. And this is our first condition, and the second condition is IA cos phi constant. So project IA components along V and along horizontal axis. So now projecting IA1 along V represents IA1 cos phi 1. So as here we have to maintain E sin delta constant, means this value must be constant. So fix like this. And similarly IA cos phi is also constant, means this term is constant, which implies fix like this. Now our IA1 values varies with respect to this IA1 cos phi, and E1 varies by maintaining constant E1 sin phi. Now current IA1 to IA2. Let this be IA2. And to this IA2 we have to represent IA2x2 drop from V to get E2. From V, maintain perpendicularly, draw IA2 axis, and now the resultant is our E2, and the angle between V and E2 is delta 2. Okay, and now increase the armature current. Let us suppose it is on this one, let it be IA5, and to this we have to represent IA5 axis drop to get E5. From V, maintain perpendicular, draw IA5 axis, and to this resultant is our E5. Okay, and again let us suppose current IA8, and to get E8 we have to represent IA8 axis drop from V perpendicular to the IA8 phasor. So from here, maintaining perpendicular, draw IA8 axis, and now the resultant is our E8. And from this diagram, now we will draw the Vn inverter vehicles. Okay, observe here that here to the V, Ia is lagging, so this region comes under lagging power factor region. From here, as Ia is increasing, observe here that Ia is leading to the V, so this comes under leading power factor region. And similarly, observe here this region to this region. Okay, here E cos delta. Okay, this is our E, and E cos delta is this value. So for lagging power factor case, means from the lagging power factor region, so observe here that as Ia decreases, E1 cos delta value also decreases. So this is E1 cos delta, and for Ia2 this is E2 cos delta, means E1 cos delta and E2 cos delta simultaneously. With increase in armature current, E cos delta value is decreasing, and from this region to this region, E cos delta value is greater than V, means as we know that Q is equal to V by Xs into E cos delta minus V. Okay, as E cos delta is greater than V, then Q is positive. So in this region, E cos delta value is greater than V, so that this comes under Q positive. So as Q is positive, here delivering case. And come to the case of leading power factor region. Okay, so as current now increases, armature current now as current increases, okay, as armature current increases, observe here that E cos delta value decreases. Okay, and from this region and up to this region here, E cos delta value is less than V. As E cos delta is less than V, Q is negative. So from this region to this region, Q is negative, and if Q is negative, you can say it is absorbing case. And here delivering case for lagging power factor region, and Q is negative for leading power factor case. Okay, now using these conditions, okay, we will draw the important Vn inverter V curves. So now let us draw Vn inverter V curves and take this as armature current and this as field current. Okay, now observe here, with increase in field current, what happens? Induced voltage increases. Now let us suppose that field current is increasing, so that induced voltage will increase. So observe here this case, here the value of induced voltage increases, means as field current is increasing, induced voltage E is increasing. Along with that, with leading power factor region, observe that current IA value decreases. So from value to like this, IA value decreases with increasing field current. And once the armature current comes in phase with V, here E is equal to V. Then, so this comes under leading power factor region. And now, upon increasing field current further, means upon increasing the induced voltage E, now IA comes in lagging with V. So now IA enters lagging power factor region. So in lagging power factor region, observe current IA. So current IA increases. So with increasing field current, now current IA increases like this. So this is the V curve, which is the graphical representation between armature current IA and field current IF. And this is the lagging power factor region. And next, observe the power factor now. Now, with increasing field current, we know that induced voltage E increases. So as E increases, IA value is decreasing. As IA value is decreasing, observe here that the angle between V and IA is decreasing. So as phi is decreasing, power factor increases. So like this, power factor increases with increasing IF and increases until I reaches V, means until I and V are in phase. So this is the case up to here. Now observe that with still increasing field current, E will increase. So along with that, here IA value is increasing, means entered into lagging factor region. As IA is increasing here, power factor angle is increasing. So if power factor angle increases, power factor decreases. So in lagging power factor region, power factor value decreases. So this is inverted V curve, which is the term between power factor and field current. And here from this graph, for lagging power factor region, Q is positive, means delivery. For lagging power factor region, Q is positive, means delivery. And for leading power factor region, Q is negative, means absorbing. So Q negative means absorbing. So now the point is here that with increasing field current, Q absorbing is increasing or decreasing. Let's find out. Take the leading power factor region. So with increasing field current IF, E is increasing. So as E is increasing, in leading power factor region, IA value is decreasing. So as IA value is decreasing and E value is increasing, observe that here E cos delta value is increasing. So as E cos delta is increasing, Q absorbing is decreasing in this direction. And with still further increasing field current, E is increasing. So IA value is now entered into lagging power factor region and IA value is increasing. And E value is still increasing, means E cos delta value is increasing. So as E cos delta is increasing, it is more positive. Becoming more positive means delivering more in this direction. So this is about the effect of change in excitation by maintaining mechanical input constant. Next, effect of change in mechanical input with excitation constant. So consider the infinite bus bar to which a salient pole type of alternator is connected, and let this be the field supply for excitation, and let this be the prime mover input to the alternator. As here excitation is constant, means here Q is constant, which implies E is constant. And we know that here P is equal to EV by XS sin delta. As infinite bus power, V is constant, and as excitation constant means E is constant, and XS we know that obviously it is also constant, and which implies P is directly proportional to the sin delta, where delta is load angle, that is angle between E and V. And the other relation what we must know is E is equal to V plus J IA XS, and Q is equal to V by XS into E cos delta minus V. So these are the three relations which we use to draw the phasor diagram. Let this be the terminal voltage V, and let this be the initial armature current IA1, and to get E we need to add IA1 axis to V to get E. So from V, draw IA1 axis drop phasor maintaining perpendicular with IA1. So IA1 axis, and the resultant is E, and the angle between E and V we call it as load angle, that will be represented with delta. As here excitation is constant, E value is constant, means locus of E will follow a circle. So locus of E is a circle. In previous case, locus of E is a straight line, because there E is limited by E sin delta constant, and armature current IA is limited by IA cos phi constant. Here there are no such constants, and the only constant present is here E. So the locus of E is a circle. Now increase the mechanical input so that armature current increases and delta also increases. Let this be the delta 2. To get E, we need to add IA2 axis drop to V. So by maintaining perpendicular, draw IA2 axis drop from V to get E. Okay, and similarly increase the current to IA7, so that to get E we need to draw IA7 axis drop perpendicular to IA7 phasor. So this is E, and the delta P delta 7, and similarly increase the armature current to IA12, and from V draw IA12 axis phasor to get E. So now observe that this region comes under lagging power factor region, because here armature current IA lags behind the V, and in this region comes under leading power factor region, because here armature current IA leads V. And if E cos delta value is greater than V, Q is positive, which means Q is delivering, and if E cos delta value is less than V, then Q is negative, which means Q is absorbing. So in lagging power factor region, observe that as armature current IA increases, okay, E cos delta value decreases, means E decreases. So it decreases until it equals to V, means this region to this region Q is positive, means delivering, and which comes under lagging power factor region. Now observe the leading power factor region. As armature current I increases, E cos delta value decreases. So it becomes more negative with increasing armature current, means Q is becoming more negative. So more negative means more absorbing, and this region to this region, okay, Q is negative, and which implies absorbing, and Q is negative in leading power factor region. And from this phasor diagram, we will get the important relations like in lagging power factor region, observe that as armature current IA increases, okay, angle between V and I decreases, means power factor increases. So as IA increases, power factor increases, means it has direct relation with mechanical input, means directly proportional to the load. And in lagging power factor region, Q is delivering. Observing lagging power factor region, as armature current IA increases, okay, E constant value decreases, means as E constant value decreases, Q decreases, okay, means here Q delivering is decreasing with increasing armature current, means it has inverse relation with mechanical input, which implies inverse relation with load. And in leading power factor region, observe that as armature current increases, power factor angle, means angle between V and I increases. As angle between V and I increases, power factor decreases. So with increase in armature current, power factor decreases, means power factor has inverse relation with mechanical input, means inverse relation with load. Observing leading power factor region that with increase in armature current IA, E constant value decreases, so which is less than V, so that Q is negative, means with increasing armature current IA, Q is becoming more negative. So Q is becoming more negative means more absorbing, means Q absorbing has direct relation with armature current, more absorbing, which implies Q absorbing is directly proportional to the mechanical input, which implies direct relation with load. So these are the important relations which we must keep in mind. And the last important topic is grouping characteristics, so which is the graphical representation between frequency and load. Okay. So grouping characteristics will look like this, and this is the no-load frequency, and this is the full load frequency at which it supplies a load of PG1, means full load power. Grouping characteristics are important for an alternator to share the load proportionately. In competitive exams, questions will be like this: if the generator is having these grouping characteristics and if it is operating at a frequency F, then what is the power supplied by the generator to the load? Suppose this is the frequency at which now our alternator is working, means operating, then we need to find here the power supplied by the alternator when it is operating at frequency F. For this kind of problems, there are two approaches to solve, that is Y is equal to mx plus C concept, and the other is symmetrical right angle triangle property. So according to this, ratio of bases is equal to ratio of heights. Okay, let us mark these points A, B, C, O, D and E. So by this concept, here Y is F and M is slope. So slope can be found by applying y2 minus y1 by x2 minus x1. So here this is x2, y2, and this is x1, y1. Okay, by this way you can find the slope, and if you observe obviously that here the slope is negative slope, okay, we get minus m, and axis here load, and which is P1 plus C. C is the intercept of this characteristics with y-axis, means with F. So from 0 to A represents the C. So by this way you can find the power supplied by the alternator when it is operating at a frequency F. Now let's see how to solve this problem with this concept. The similar triangles here are ABC and AD. So ratio of bases means ratio of BC by DE is equal to ratio of heights. So height of triangle ABC is FNL minus FFL. By height of AD triangle. AD triangle is this one, means FNL minus F. So here BC is PG1 full load power by D is the required power. That implies the power supplied by alternator when it is operating at frequency F is given by F no load frequency minus F by F no load frequency minus F full load frequency into full load power. And the other problem might be like this. They will give grouping characteristics of two generators. So let this be the grouping characteristics of generator G1, and let this be the grouping characteristics of generator G2. So question might be asked like this, that if the two generators are connected in parallel to operate at frequency F, then what is the share of generator G1 and what is the share of generator G2 of total load P? Means let us suppose if the generators are set to operate at frequency F, then the share of generator G1 be P1 and the share of generator G2 be P2, which implies that P1 plus P2 is equal to P total load. So of total load P, here we need to find the share of generator G1 means P1, the share of generator G2 means P2 of total load P. So this kind of problem can also be solved by the similar approach, and in few numerical problems in place of F it might be given speed regulation. So this is how we need to solve the numerical problems on grouping characteristics. So this is all about alternators, and if you like this video and my presentation, please like and subscribe. If you subscribe, you will get all the notifications of my latest lecture videos, and I am planning to do lecture videos on all GATE and engineering service technical subjects of electrical engineering paper. And the reason behind making all these lecture videos is to make available all the subject videos to the students who can't afford to take admission in coaching institutes and who wants to succeed in their core domain. So if you share these lecture video links in social network so that it might reach to those who wants to succeed in their career. So please share these video links in the social network. Thank you, and thank you for your interest in learning these subjects, and thank you for your patience. Thank you, and see you in next lecture.